Welcome. In this video, we're going to learn about the components of neural networks. Topic include neuron, perceptron, and multilayer perceptron. So let's get started. Okay, so let's talk about some inspiration for the neural network, and that is from the human brain. And nature had inspired with many inventions. Think about the shape of the hawk, inspired the development of the fighter planes here. The white flower Velcro give some inspiration to our curtains. Usage of Velcro tapes, and also the robotic arms are taking a lot of inspiration from an elephant trunk. But perhaps the brain is nature's ultimate inspiration for invention. And all of these components have its meanings. So you have input represented X, 1, 2, 3. Each of these arrows here is represent a weight associated with those inputs. The operation of the LTU can be break into two parts. This weighted sum part, right, represented by a summation here. And then the what called activation or the step function here, represented by a step function here, and with a mathematical sigma to represent the activation. And then you have your output. So we're going to use this representation, graphical representation, throughout the rest of the slide. So keep in mind those in there. All right, so next from this LTU, Frank Rosenbach in 1957 invented the simplest form of a neural network architectures, the perceptron. And the perceptron, as you see here, composed by a layer of the LTU, and each of the neuron connected as an input called input neuron. And we also have a bias neuron to generate, some shift bias into the network. And this called a input layer. Why? The output layer will produce the output. So you can see here, they have at least two layers in the perceptron. Now, perceptrons was great talk back in the first wave of development of artificial neural network. But the problem it is a linear networks and linear system is suffer from the XOR classification problem. What is the XOR classification problem? So you all know exclusive OR here. And when the input are the same, it outputs 0. And when the input is different, it outputs 1. So if you plot this in a Cartesian coordinate, you can see when both the inputs are the same, these are 0 or the square. And if it's 1, these are the triangle. The problem with this is that if you use a linear combination between the output, what happens is you move from 0 to 1 here, and both of your feature 1 feature is 0. You have nothing to do except increase the weight of the second, or weight W2, right, from here to here. However, from here to here, with the x1 equal to 1, and you want to go from being 1 to 0, you have to decrease the weight, W. So this creates a conflict. And in short, no linear system can be able to separate these four input into classes. You can see here graphically, you cannot fit any linear function to separate these into two classes correctly. So that's for a long time was an issues, and trying to figure out the way to do it. And eventually they has, but it cost them an AI winter to figure this out. And the way to do this is to stack multiple layer perceptron into what we call now a multi-layer perceptron. And that's where we're going to get at, multi-layer perceptron, or MLP. So multi-layer perceptron consists of a input layer, just like the perceptron, and then it consists more layers called hidden layers. So these are the layer in between the networks, which we would not be able to observe, right? One can see the input and the output, but the layer in between is hidden. That's why it's called hidden layers. And you might have include, with biased neuron and so on, part of the network. And if you have a multi-layer perceptron with more than two hidden layers, then we have a deep neural net. Here we go. Now we have a definition of a deep neural network. Now, how do you represent this multi-layer neural net, right? So we use similar graphical representation than we had before. Each of the node in a hidden layer will be two parts. The summation one, so Z is the response value for the weighted sum, and the weight going to be represented by each of the arrows here, mapped from the input to the response value Z. And then we also have the activation part, where you apply a function sigma through the response value Z to obtain the activated value A. And so on and so forth, true for every single node into our network, right? So the FOSDEP notation, the upper number would be denoted at the layer number, right? So this is the lower part will be the node number, right? So this this is the responded value Z for the first node of the second layer, right? And then we have the output, Y hat, predicted output. All right, so let's dig down into some quick calculation. How do you map from the input X into the predicted output Y hat? Okay, so first we have a weighted sum from X and plus some bias terms here, right? It's just a number, and then you obtain a response value Z1 of layer 1, and then you take that value and you apply a sigma functions, and then you end up with the activated value, right? So imagine I just started a chain, and the output of this chain, I'll feed it to the next link, and so on and so forth, right? Same with the Z2 here. Okay, maybe I show in this case. Z2 here is the weighted sum between W2, which is all these weight going to Z2, time X, which is the input, plus B2 of layer 1, and then you do the activation for A2 of layer 1 as well. And you do the same for the other two nodes. So at this time, you have value A1 to A4 of layer 1. Next, what we do is that we're going to combine this value, right? Remember, neural network is about combination of different layers. So here we are. We're going to transform from all the A's into the new Z. So Z1 of layer 2 will be the weighted combination of all the A's from layer 1 plus some bias term. And then you do it again with the sigma function. And finally, the predicted value is the A1 of layer 2. Okay, so the math, pretty straightforward, I think. But can we do better? It just looks like a lot of equations there. Can I vectorize them, stack them vertically? So if I have one function here, I have calculated for all the Z, right? So if you notice, if I stack all this Z together, all this number together, I get a vector Z. So Z of layer 1. Now if I stack all the weight W, I have a weight matrix. And if you look at each of these arrows again represent a weight associated with the input. And so if you count, these are 3 weight going to this node, 3 weight going to this node, so I have 4 nodes. So this weight matrix will be with dimension 4 by 3, because based on the node that we have. And same with the bias term, B1 to 4 of layer 1, we now have a vector B. So all of these calculation can be represented by a single linear algebra equation, Z1 equal to W1x plus B. Ain't linear algebra beautiful, right? The painstaking that you have done with linear algebra may pay off here for the understanding of the neural net. Okay, so for the activation function, we do the same, and we end up with activation vector A of layer 1 and the sigma activation function of response value Z1. So you can rewritten as such. Pretty cool. We reduce the number of equation we have to do using vectorization. All right, so what is the dimensionality of these vectorized components now? Right, so you have the same equation again, z1, which is all this number, and you kind of can cheat yourself. If you look at here, as a 4 number, the dimension of z1 must be 4 by 1, right? So that was an easy one. But, well, what if w1 here, right? And then again, you depend on the network architecture that you design, you might have different dimension for w here. So W is the parameter of the network, something that we'll have to learn later on. But now we should learn quickly the dimension of W, not the actual value of W, right? So if you do some counting here, you say, okay, there are 3 arrows going to here, and then same 3 arrows to go to 4 nodes. So with that, W may be 4 by 3. And that was 4 by 3. The input x is, well, there are 3 inputs, so there's be a vector of 3 by 1, and you know the multiplication works out because the internal components match, so you can be worked out to, you do matrix multiplication here, it end up with a 4 by 1 vector, and then you add the 4 by 1 with a b, dimension of b here, right? So for the activation function, sigma is here. You put the response value z in, and now you have an activated value, right? So the activated value, this activation function did not change the dimension of the input, so the output you have the same dimension. And you do this again for the second layer. So the second layer, slightly different, right? Because now your w is 4 going in, so it's 4 by 1. The a is 4 by 1, well, actually W is 1 by 4 because they're going 4. Excuse us. Even I get confused sometimes. But the W is here is 4 by 1 because there is 4 weight go into 1 node. And then you can do matrix multiplications here again, and you end up with a single number, right? It's a single number, and you add a B here and then with Z. Now notice I have only single nodes here. If I have multiple nodes, then this dimension will be changed a bit, right? You have 2 here if I have 2 nodes, 3 here if I have 3 nodes, so on and so forth. So that's to give you an example to see how it is changing from one input to another input, right? Now, so far, I only do one single example, X. Well, what if I have multiple examples? How do I do it then, right? So if you have multiple examples, in this case, M examples, you would end up with going from the input all the way to the activation of the second layer and predicted some value. And you can calculate this using a for loop, right? I from 1 to M, which undoubtedly many of us will write because we train computer science and we can write for loop to represent all our calculation, right? So all of these now have an extra notation here for the example that it come from, the example I. Right? Now, this may look pretty good to you, but we actually can make it better. And the way we make it better is to apply more vectorizations onto this multiple example. So if I set each of the training examples side by side, I would have M of them. So this, I would make it into a matrix, and this matrix have M columns, each column for a example, and the row will be N because it have N dimension. So N's here, N0 in this case because it's an input layer, right? And then I'll do the same for the response value Z, right? So if I have Z1 of 1 and Z1 of 2 all the way to M, I can make it into a Z matrix with dimension N1 by M. So you have M column. So this N1 is the number of node in a layer 1. Right? So depend on the number of layer that you might have different Z. Remember, each Z is in each node, right? So N1, Z, is the number of node in that layer. Same thing with A, right? So the nice thing about having this vectorized is that instead of writing this for loop, we can vectorize it into just single calculation. Now the Z become matrix Z. Well, the W stayed the same, is matrix W. The X now is input data X, and the B also. There's interesting things about B here that I noted is that B was actually won't expand from the a vector form to the matrix form. In fact, matrix B here is just a replication and replication of vector B. And if you write this in in a programming language, this would typically call broadcasting of the matrix. So you see that when you write. But B here is just the M replication of vector B. Right? And we'll do the same for A. So A would be just the activation of Z. Z2 would be the same thing again. And you have matrix A2 would be the activations of Z. Okay, simple enough. So now we actually know how to represent passing signal from the input data all the way to the output being just A2. So you now know how to do this from end to end, right? And if you need a tip on the dimensionality of the neural net, here I provided to you. Always remember this. The weight dimensions always have the same dimension as the current layer by the number of nodes in the previous layers, right? And then Z, A, and B would have the same dimension, which is the number of nodes in the current layer times the number of example in your training batch, M. Note that B is consisted of replications, right? So hopefully, well, there'll be quiz and tests about this. So make sure you really know the dimensionality of network, and this also will help you to have a good understanding of the implementation of the network as well. So this is, I think this is quite important for you to know this information, right? All right. Next, we're going to talk about activation function. I know I've been teasing you with that sigma function, but what exactly does that sigma function actually do, right? So we have a few activation function at our disposal. So number one is the step function that we see earlier. It'd be 1 if it greater than 0, Z greater than 0, and if it less than 0, then it's have 0, right? So input is Z and output is A. So it's just thing that happened in our little node that we see earlier, right? Passing from Z to A. Okay, and we have sigmoid function. You might seen sigmoid function before in, logistic regression and things, and that's a formulation. Plug in the value of Z. This is the value of A we're going to get back for activated value. 10H, similar. Oh, the sigmoids here represented by this green curve. Very nice green curve. And it's always going to be between 0 and 1. So it's pretty great for probabilities. Now the 10H is similar to sigmoid, except that it stretch the output from, instead of 0 to 1, is -1 to 1, right? And then you notice also it follow when the Z close to 0 here, it pretty straight or represent an identity function. We'll talk about that. And finally, also mention ReLU, which is called rectified linear unit. And the ReLU is very similar to the hinge lot function that you might have seen in SVM. So what ReLU does is that when it's not activate, or when Z less than 0, it's just 0. And when Z is greater than 0, then it's just Z, right? It's a pass-through. And you can write it at a mathematical MAC function between 0 and Z. So that's what it is. Okay, so question is, why activation is necessary? I'm doing fine without it. No, you won't. And so without activation function, each layer will be consist of just linear operation, dot product and addition, the bias term. So the layer can only learn linear transformation of the input data. Adding a deep stack of linear layers, well, you still implement a operation of linear function. So if you want to incorporate nonlinearity to gain a richer representation of the input data, you have to employ activation function, because these are nonlinear transformation. Right? So you can think about it. All the neural networks doing is trying to describe the feature using a affine or linear transformation controlled by the weight W of the learned parameters, and then followed by a fixed nonlinear activation functions. Right? So that's the gist of it. So if you want to learn your weight parameter using activation function, using some sort of gradient learning, gradient-based learning here, there is some consideration that you have to take. So first of all, the step function actually won't work with a gradient because it have a zero derivative, so you can't really do much with it. The sigmoid function and other functions here have well-defined non-zero derivative. If you can see here, the sigmoid, the tanh, and even the ReLU have non-zero derivative for the most part. So it's allow gradient descent to make progress. And especially ReLU, if you see here, when it's active above 0, the derivative is large and consistent, right at 1, right? So these make good for gradient-based learning, except the step function, right? Now I want to also introduce you to the softmax functions. It's a really cool function. Every time that you want to represent a probability over a discrete variable with n possible value, you may use the softmax function. And what it does is that in the classification system, it would produce output which all sum up to 1 of n classes. Really, really nice property. And the way it does is it exponents and normalize the output, right? So you have some input here, it was exponent, and then normalize it over all of the different classes here, right? So each of the z here represent a class I, which is a log probability of when the label equal to I, given the data, right? And then the nice thing about the softmax, if you notice, if you take in the logarithmic of the softmax, this division become a subtractions, and so it is just, and then the exponent and the log cancel out, so you end up with just zi minus log of the sum. And this log term is approximating a maximum of the j here. And the intuition about this is that when you try to maximize the log likelihood here, flashback on the probability theories here, guys. If you're trying to maximize the log likelihood here, what you have to do is this term would definitely contribute greatly to that maximization. But remember, you're also trying to minimize this term, right? So minimize this term, meaning the intuition behind this is that you're trying to give graded penalty to the highest probability, but that was in the incorrect class. That's what this term represents, right? So while you're trying to maximize this, you're trying to minimize or penalize the highest confident but incorrect terms, right? So, and you can think of softmax like generalizations of a sigmoid function. So sigmoid for binary variable, softmax is for higher than 2 variables. And finally, you can think of softmax is a softened version of the argmax that we see all the time, right? So argmax return 1-hot factors. Okay, so that's some quick tip on activation function. We're going to return and talk more about this here, but the step function won't work with gradient-based learning, so we're not going to really mention it a whole lot anymore. ReLU is fast to compute and easy to optimize because, as you see, it's pretty similar to the linear functions here, and then you have the 0 when it's not activated. So this behavior pretty close to linear function. Both sigmoid and tanh are both saturated at 1. And why is this a problem? We're going to learn in the next videos. And the tanh are easier to train than sigmoid because they are it is very similar to a identity functions at this here when the z near 0. And finally, for classification tasks, use softmax. For regression tasks, you don't need to use activation function. All right, so in summary, the network architecture designs. In general, most neural network will be arranged at a chain structure that we see earlier with the linear algebra equation, and each layer being a function of the layer that before it or preceded it. The main consideration that we have to have designed this network is choosing the depth of the network. How many layers do you need? And the width of each layer. How many nodes in each layer? The deeper network typically have fewer unit per layer or less node per layer. Certainly carry fewer parameters, but they tend to be harder to optimize. We're going to find it the hard way later on in other videos. And the ideal network architecture for a task must be found through experimentation and by monitoring the validation errors, right? More reason to break your data set into validation. And that's how you can choose the right architecture for your network, right? So that is all you need to know for neural network. And the next time, in the next video, we'll learn about how actually find the weight W that we were talking about. Optimize weight W, how to train the neural networks. Until then, take care.